No. Please push.
Which video again?
Please, can you all mute yourself and just close your video?
I must stop video. Stop showing my face. Is that the woman? No.
Please, can you switch woman? What kind of stupid question is that? I think we are here to joke. Okay, good morning, everyone. We are back. So I said we'll be talking on the development of atomic theory and we'll be talking on development of atomic theory and atomic structure. Now, why do we need to look at the atomic theory or the structure, how it's developed? We know that the description of theories or models of an atom, helps us to understand how scientists developed the atomic structure. At the end of the day, why is it that you have the proton in the nucleus and the electrons surrounding the protons or surrounding the nucleus? Then this is just to help us understand or to help us think about, involving or modifying an existing theory. If we understand that scientists before were able to, through evolution, through modification of what is existing, and that is what has brought us or gotten us to where we are. So it's just to help us know that we can learn new things, we can also modify existing things and we can make new discoveries. So that is the reason. Who is that? I'm going to be sending you guys out of this class.
Oh, what is the second name? What is the second name?
I think I have your time. So we are going to be starting with the earlier scientists that developed the atomic theory. First, we'll start with Democritus. Now, this is going to be like a story lecture. The way they tell us the stories, our grandparents tell us story. We sit down, they tell us what is happening. So it's going to be flowing that way, so that I will just mention the most important thing or the most developments by each of the scientists. Now, like I said, this particular lecture is to just, bring our mind to understand and to think how science evolved and how science is evolving. Like I said before, it helps us to learn new things. It helps us also to modify an existing things and makes us to recover new ones. Now, there are steps involved in all this, but we are not going to go into it. I know that in our secondary school, we looked at scientific steps, in the steps or the methods involved in scientific analysis, where we say, first of all, we form our question, we perform a background research, we create hypotheses, we design an experiment, and then from our experiment, we can make our conclusion and share our results with others. Then from your results, people can now modify what you have done, by using, they can put one or two things to make what you have done to come out better. Let me put it in that way. Now, in the history of atom, thank you so much. In the history of atom, Democritus was the first scientist who proposed the existence of atom. Now, listen to me. Democritus is a philosopher and a Greek philosopher. What this means is that this particular proposal, let's put it that way, from this great scientist is only based on logical evidences. There is no experimental backup to all that we are going to hear that he said or did. He did not go to the lab. He did not carry out any experiment. He just assumed. Being a philosopher, he just thought, okay, if this is like this is what it is. So we should know that. Now, what Democritus did was he pounded materials, the way you pound in your mortar. I'm not saying that he used mortar. I'm just bringing it down to where we are so that we'll understand it better. So he pounded it into smaller and smaller and smaller particles. And so he referred to the fundamental building blocks of atom as atomos. That is a Greek word. This atomos means indivisible. He believed that the universe, when we talk about the universe, we talk about matter. We talk about everything that ever exists. Human beings, our clothes, our hairs, our materials, our electronics, they are all matter. So he believed that matter is made up of indivisible units. And this unit he called atoms. So that is his belief. Like I said, remember that this scientist, Democritus, worked in a guess. There was no experiment to back up what he has said. He just assumed, okay, since I am able to this thing is uncuttable. I can always put it into smaller till infinity. And this was accepted because at that time, so many things were accepted based on logical reasoning. But Aristotle, after much years, over 2,000 years, came and disagreed with this man. He called it a ridiculous idea. He said this is quack. He said this is just a guess. But you can always divide anything to whichever level you want. You can divide forever. For as long as there is something that's existing, you can divide that into whatever, however you want it. So, also Aristotle is a philosopher. His own argument is not based on experiment. It's still a guess. So both of them, to me, they are the same. They are on the same category. But you know what? Because of Aristotle is famous, his own idea was immediately accepted. And that of Democritus was put together, and scientists start believing that you can always, divide matter forever. You can divide it forever. Now, here comes a great news for us scientists. Sorry, I didn't know when I touched that. This class must hold. I don't know what is happening, but the class must hold and we'll finish. We'll be telling our stories and be going. Okay, sorry about that. Okay, so like I said, in Democritus, he said that there was a limit to how far you could divide matter. You would eventually end up with a piece of matter that you could not cut. That is why he said that it is indivisible. Like I said, somebody now said, you are crazy, you're quack, you're this and that. He disagreed with Democritus, and that person was Aristotle. But the thing about Aristotle is this. He didn't even back up his findings with an experiment. He just said that you can divide anything forever without no backup. But like I said, those times were the times you're famous, it depends on who is who. And because Aristotle is more famous than Democritus, his idea was accepted and the idea of Democritus was rejected. And so that's continued. But the limelight that came into the theory, into the history of atom was in late 1700, when John Dalton now carried out, not that he carried out a new experiment. Before now, the chemical laws were in existence. That is, the law of conservation of mass and the law of constant proportion. The chemical laws have been in existence, but no one has ever tried to verify this law by carrying out an experiment. So Dalton carried out an experiment to actually back up these laws. I hope you guys are understanding. Dalton did not carry out a new experiment entirely. No, he based his work on looking at, okay, these are chemical laws that are existing. Let's see what happens. And so he carried out an experiment to study how elements join together to form new substances. And that is all about the chemical laws. So his idea, he made some proposals. He made about 5 proposals. One, from his experiment, he found out that matter is composed of extremely small indivisible particles called atoms. Now, remember that this was what Democritus has already proposed, though there was no experimental backup. What is it in this chart that you people are having 16 now? Okay, I thought someone is stranded somewhere. Now again, the second one was that atoms of a given element are identical in size, mass, and other properties. The third postulate was atoms can neither be created nor destroyed. The fourth was that atoms of different elements combine in simple whole number ratio to form chemical compounds. And the fifth was that in chemical reactions, atoms are combined, separated, or rearranged, but not destroyed. We are going to be looking at these 5 postulates by John Dalton. But again, we should also have at the back of our mind these postulates. How many of them were debunked? That is, how many of them were rejected based on other scientists' experiments? All the 5 of them, are they still true? Or is there any one of them that has been debunked? That is what we are going to be seeing later. But let's go on and see what happens to this Dalton's postulates or Dalton's thoughts. Remember, like I said, these are all about trying to support the law, chemical laws based on experiments. It's not that he carried out a new experiment altogether. Now, there's one particular thing associated with Dalton, which I want to mention. He envisioned atoms as solid hard sphere, like billiard balls, like billiards a ball. So he called, usually you can call his model the billiard ball model. If it is not a Dalton, anywhere you see that, that is what it means. It means the Dalton's model. What are the limitations of this Dalton's atomic theory? Remember when I started, I told us that the reason for this is for us to learn new things, to help us think, and to also help us understand how science evolved and how science is evolving. What do we need to understand there? One, that you can learn new things, that you can modify existing things, and that you can form new ones. Now, Dalton has found out something, but there are limitations to that. And these limitations are being backed up by what? By experimental evidences. I hope the story is not too scientific. Can you go to the chat box and tell me? Because I want to tell it like a story thing, so that you don't need to cram anything. You just need to flow and understand who did this and what the person did. So go to the chat box and tell me. I want it to be like story, once upon a time. Because I know that the stories that your grandparents told you how many years ago, 10 years ago, you can still remember them because of the way the story were told. So, is it a story thing, or are we going scientific? Good. We are following. Good. I want everyone, okay. It's story like good. That is what I want. It's story like, because I don't want to bore you into reading all of these things. It's a whole lot, and you have a lot of things to do. Now, let's look at those limitations. I hope you still remembered all the 5 postulates by Dalton. The first, we say that matter is composed of extremely small indivisible particles called atoms. This has been debunked. It's no longer true, because we now have the discovering of subatomic particles. So we have something that is smaller than atom now. We have the protons, we have the neutrons, and we have the electrons. Now I'm going to tell us the scientists that discovered each of this just here, but we are still going to look at what experiment they carried out, if time permits us. Proton was discovered by Ernest Rutherford. He discovered that there is a positive charge, and it is dense, that is in the middle of the atom. That is where you have the nucleus. We are still going to look at his gold foil experiment to prove this. Now, the neutrons were discovered by James Chadwick, while the electrons were discovered by J.J. Thomson. All of these 3, we are going to see how the experiment was carried out. But at least you now know the scientists that discovered each of these subparticles. And because these subparticles are smaller than atoms, that postulates by Dalton that matter is composed of extremely small indivisible particles could no longer hold, is no longer true. Because you have found something even in the atom that even is smaller than atom. Now let's go to the second limitation. Now, the second limitation. Now the postulate says all atoms of the same element are the same. We know that with the idea of isotope discovered by Frederick Soddy, that this is no longer true. You now have atoms of the same element having different masses because they have different number of neutrons. So you can no longer say that the atoms of the same element, they are the same. You have now isotopes. For example, hydrogen has 3 isotopes. Helium has 2. Lithium has 2. Oxygen has 3. And all of these isotopes are different from each other. For example, we look at protium in hydrogen. It is different from deuterium, and deuterium is different from tritium. So all these things, they are not the same. Yes, they are atoms of the same element, which is hydrogen, but they have their different neutrons and they have their different masses. So they have different number of neutrons. Now again, we are going to go into isotopes because the way the syllabus is now, you will not have time to look at isotopes in your year 2. So what are isotopes? We define isotopes. Remember, we still have 3 other postulates. We are number 2. So you don't be carried away. We still have the other 3 to deal with, but we'll be fast about it. Now, there are atoms with the same number of protons, but different number of neutrons. Now, when we say that atoms have the same number of protons, your number of protons is the same as your atomic number. Then your mass number is your number of proton plus neutron. And so you can also define isotope as atoms with the same atomic number, but different mass number. We have example here. You have your chlorine. Chlorine has atomic number of 17 for both chlorine 35 and chlorine 37, but they have different mass number. And the different mass number is because of their difference in the number of neutrons. Now, oxygen again has 3 isotopes. The atomic number is 8, while the mass numbers are 16, 17, and 18, respectively. So that is what the isotopes are all about. Now, we can actually calculate relative atomic masses from the composition of the isotopes, because you have those isotopes they are of the same element. And remember that they are usually natural, they usually occur in nature. And so their mixture is what you can use to calculate their relative atomic masses. So when you're dealing with isotopes, you talk about their relative atomic masses. And what is it about these relative atomic masses? Remember, like we said, it's going to depend on if you have 3 isotopes, the 3 of them. So you have elements, the abundance of the isotope in nature. Then you calculate the percentage of each of the isotopes to give you the relative atomic mass. We have an example here. Bromine consists of 2 isotopes. You have 50% of bromine 79 and 50% of bromine 81. Calculate the atomic relative mass of bromine from the isotopes. Now, to calculate that, remember we said it is the combination of the isotopic composition, the two of them. So what you need to do is the percentage occurrence of each of the isotope times the mass number of that isotope plus the percentage of the other one times the mass number divided by 100. That will give you the relative atomic mass. So if you have 3, you're going to have 3 of those percentages combining together to give you the relative atomic mass. Now I have a question for you. Quickly calculate the relative atomic mass of silver. Silver consists of 51.4% of 107 and 48.6% of isotope 109. Calculate the relative atomic mass of silver quickly in less than 30 seconds. I did not calculate it, so if you give me a wrong answer, I don't know. But just be quick about that. What do you have? I'm here at your chat box. No one has done it. What is the answer? Don't worry about the slides. Once I'm done now, I know why I've not given you slides. Once I'm done now, I'm posting it to the Telegram. I'll post the slide to the Telegram. So listen. I told you when the first day I started this class, listen. This is the slide that I'm going to give you. So don't copy anything. You can just jot what is not on the slide. But to copy the slide, no. 108, did you approximate? The person that wrote 108, is it by approximation? Just give me the true value. Don't approximate so that I will know if you actually know what you're doing. That one is not. Meet your class rep if you've not been added. Okay. Okay, so I think at least most of you got the correct answer. So let's move on. There's no time. Remember our story? We are talking about the second limitation. Now let's go to the third limitation, which is number 3 postulate. Number 3 postulate says atoms cannot be subdivided, created, nor destroyed. Again, the concept of nuclear reaction has made this not to be true, because now we have radioactive elements that can decay and break down to form other elements. For example, here, carbon 14 is a radioactive element. It can decay to form nitrogen. Nitrogen is a new element altogether. It's a new element altogether. And you have the beta particle released. So saying that atoms cannot be subdivided or created nor destroyed can no longer hold because of the radioactivity or because of nuclear reaction. So there are some elements that are radioactive that under some certain condition, they can actually decay or they can actually break to form a new element. So you see now that we have 3 limitations. Now that brings us to this question number 5. My question now is, out of the 5 postulates or the 5 points of the Dalton theory, which ones are still true and correct? Is it all of them? Is it number 1, 2, and 5? The limitations I gave you are from I just followed the numbering. I gave you 1, 2, 3, so I didn't jump any number. Is it 4 and 5? Is it 2 and 3? Which ones are still true and correct till today? Can I see your answer on the chat box quickly? Which ones? The second question, please. No, it's not only one of them. Correct. Correct. Stop writing your name. Answer my question. Good. C, correct. Correct. Is C. C. 4 and 5, they are still correct, because let's go back. Let's see what 4 and 5 says. Look at your 4 and 5. It says atoms of different elements combine in simple whole ratio to form chemical compounds. For example, your CH4, your methane, or take any combination. And that is why when you have your empirical formula, you bring it to the lowest whole number ratio. So that is still true till today. In chemical reactions, atoms combine, they separate and they rearrange but not destroy. Exactly, because when you carry out a chemical reaction, that is where the balancing of equation comes in. Whatever you have on the reactant side, you always have in the product side. If you have 5 molecules of silver here, you must have that 5 molecules of silver in the product side. And so atoms are combined, separated, or rearranged, but you cannot destroy them. You can actually react a silver, maybe silver nitrate with something, and your product, you get silver chloride. Whatever you're having in your product is a rearrangement. But the thing is that you're not destroying anything. It's just a rearrangement. So 4 and 5, correct. 4 and 5 are still through till today. Now, when I started with Dalton, I told us that the Dalton's theory is based on, studying the chemical laws. It's not that he did a new experiment, no. So his theory is based on the law of conservation of mass and law of constant composition. So when we say the law of conservation of mass, the law of conservation of mass, like we know, like here you have the total mass of matter in the left-hand side must be total mass of compound or matter in the right-hand side. Now, we know that burning is a chemical reaction, but when you burn this particular mass of matter, at the end of the day, you must get this particular mass of product. So the mass of the product in a chemical reaction must be equal to the mass of the reactant. That is all that the law of conservation of mass states. The mass on the product must be equal to the mass on the reactant side. Now let's look at an example here. You have atoms of element X and you have atoms of element Y. Just you can figure out maybe hydrogen and water here. Then your compound is going to be hydrogen combining with oxygen will give you water. So if I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16 of element X, I must have 16 of element X attached to 8 of element Y in a simple whole number ratio. That is what the law of conservation of mass is. Okay, good. We have a typical example here. You see that 2 molecules of hydrogen reacts with 1, or 2 moles of hydrogen reacts with 1 mole of oxygen to give you 2 moles of water. This is what it means. You have your 2 moles of hydrogen here. You have 1 mole of your oxygen. It's reacted with 2, it gave you 2 moles of water. But if you look at this, you have how many hydrogen here? If you count it, 1, 2, 3, 4. 4 hydrogen atoms. You still have 1, 2, 3, 4 hydrogen atoms here. You have two oxygen atoms in the reactant side. You still have 2 oxygen atoms in the product side. So that is what it means by law of conservation of mass. So when you get the slide, I also have some examples for you to actually support the law of conservation of mass. Here, you heated 10 grams of calcium carbonate to produce 4.4 grams of carbon 4 oxide and 5.6 grams of calcium oxide. If you add 4.4 plus 5.6, it's going to give you 10.0. So you have the mass on the reactant side is equal to the mass on the product side. There are some other examples here that I want you to look at when you get the slide. I'm going to give you the slide. Now, remember our story? Dalton has not told us, he just told us, he hasn't told us anything about, we've looked at the limitations when he said that atoms is the smallest unit of any matter, which I said with the discovering of your electron by J.J. Thomas, the discovering of your proton by Ernest Rutherford, the discovering of your neutron by James Chadwick, that those things they are no longer true. Now, how did J.J. Thomson discover that you actually have a subparticle in the atom? Now, I may not be going through the what do you call it? Your slides, but just listen to me. Oh, I missed one thing here. Okay. Here we are together. Now, I want to go back to something. We started with Democritus and Aristotle, which based their argument on logical basis on what we call a guess. We came to Dalton, and I remember that I told you, though Dalton carried out an experiment, his experiment wasn't new. His experiment was based on the chemical laws, which were already existing. He was just trying to use it to just back up his postulates or his theory. Now, where the actual experiment started is from J.J. Thomson. So these are where you have the experimental evidence of atomic structure. So all the things we'll be talking now is actually experiments that are carried out by the scientists will be mentioning. These are new experiments. It's not that it's already existing and they are trying to use it. No. They actually started this experiment from the scratch. We are going to start first with J.J. Thomson. Like I said, I'm not going to bore you with all the things there. I'm going to tell you the story, and I know that you're going to understand the story. Now, for the first time, the first time that it's been proven that atom is not totally indivisible, but that atom is made up of smaller subparticles. In this case, we'll just be looking at the electrons, because that is what J.J. Thomson actually identified. Now, he used what we call the cathode ray tube in his experiments. What is a cathode ray tube? It is a big tube glass sealed all over. And what happens? They pump out all the air. So the inside is an inert. It has an inert environment inside. So you have this. This is the cathode ray tube. You can see that this is sealed, and this end again is sealed. And everything inside, there is no air inside. So how did he carry out this experiment? Now, he concealed it with 2 pieces of metal. These 2 pieces of metal are the anode and the cathode. And like you look at them, they have charges. Now, he now connected these 2 pieces of metal to what? To a power source. And you know that your power source will always have a negative end and a positive end too. He connected it to this power source. When he connected it to this power source, he found out that when he on the source, please, at this time, this one has not come in. These plates here, where you have, this is the metal. I'm going to be explaining it one step at a time. We are just on this metals here. Now, when he connected it, he found out that a ray went straight from this cathode and moved straight to the end of the tube. And he saw something glowing there. He didn't know what that thing was, but he saw there is a glow, and that the thing went straight to the end of the tube. That thing was electron moving, rays of electrons. But he did not understand that those were electrons. So what did he do? He wanted to be sure of what is happening. So he now took 2 pieces of plates made up of, 2 metal plates made up of a positive, this plate, the blue one, negative and positive charges. He placed them above, that is one at the bottom of the tube and the other one, the negative one at the bottom of the tube. Here it is the other way because the other side of the tube is facing the other way, but whichever side, just know that he placed each of them opposite each other. The negative charged plate opposite the positive charged plate. Now, when he did this, he now again on the power source. When he on the power source, he found out that the same ray, he found out that the same ray didn't go straight again, but it's when something bent, it bent a bit, going towards the positive charge. the positive charged plate, that is this plate, he saw that the rays, instead of going straight, the first time he did it, he found that now, okay, when that ray got to this stage, it bent and moved towards the positive plate. He now assumed, if that is the case, that means that something that is in that ray is actually carrying a negative charge. And that is why it is attracted to the positive side of the plate and is moving away from the negative side of the plate, because negative charges will repel each other while negative and positive will attract each other. Now, he still wanted to be sure of what his guess is all about before he will make his conclusion. He now used a magnet. This magnet you're seeing, this one that has south and north, is a magnet. He now used a magnet and placed the magnet in between the cathode, the ray, the tube. He placed it in between the tube. And now on the power source. Usually, when you place a magnet, there is a particular direction that magnet will go. You will know that magnet is actually, whatever that is going is actually a negative charge. There is what to expect. So it was a positive charge in the presence of a magnet because of how the magnet was, the direction of the magnet. Now, J.J. Thomson now concluded that this ray is made up of a positively charged particle, and that particle is made up of, something that is tiny, as smaller than the hydrogen particle, because at that time the hydrogen is the smallest particle. But in order to be sure, what he did was to actually use other metals to support this experiment. And for each of the metal that he used, the same result was obtained. And so he now concluded that, since everything is made up of atoms, even the plates that he is using, they are atoms. That means that there is something in that plate that is that has a negative charge, so that when he now put on the power source, that the ray, that negative charge starts coming out as a ray. And that is why he is having the result that he's having. Now and again, he concluded that particular thing that particle has a negative charge. But he now thought of it. How is this negative charge positioned in an atom? Atoms are stable. That means that it must have a positive charge somewhere to keep it stable with the negative electrons. And so he now assumed I'm going to explain it. He used the Plum model, but I'm going to explain it to us, we in this part of the world. Just picture your pizza. The dough of the pizza is circular. Yes, picture that everything in that dough is having a negative charge, and that is your electron. Now, when you have your pizza, you see those is it pizza that the dough? Now the where the meat is, those spots in the middle, the way it's scattered, depending on your money. It depends on, if you're buying 2,000 naira pizza, they will just give you like maybe shikiri 5 pieces on it, circle. They will not put, this is it meat or whatever, the pizza tin, and they will put it there. Good. If you buy 10,000 naira own, the number will increase. But just picture this as the dough without this the things inside. Then your dough is made up of the positive charge spread over everywhere, the sphere. The positive charge is spread over the dough. That is the roundish pizza. Now, those things inside that you now see the reddish color in your pizza are the ones having the negative charge, and that's the electron. It is only in this way that he was able to prove that atoms are stable, because there is a positive sphere and there is a negative negative points here. Now and again, you can picture that as your chocolate chips in an ice cream. Your ice cream, all your ice cream will have the positive charge. And the chocolate chips, you know, the chocolate chips will now be small, small. Those are the electrons, which are having the negative charge. But because there are two opposite charges, they are stable. So that is what he came up with. And so he now said, okay, good. With this plum pudding experiment, he now concluded that actually there is a negative charge particle in the atoms, which are smaller than hydrogen atom. Hence, he referred to that as the electrons. That is how J.J. Thomson was able to prove that you have electrons as subparticles in an atom. Does that make sense? Let's go to the chat box. We just have the Ernest Rutherford and James Chadwick to deal with. Does that sound good? Can you respond in the chat box? Does it sound good? Is it like a story that you can tell, that you understand? Is it like a story you can tell? Even without going back to your slides, should be able to tell some stories about how the atomic structure developed till finding an electron. Let's just stop with where we are today. You can boldly tell the story. Okay, this is how everything came. At least we've known how the electrons are now. Then we can now know we'll now go to the protons, and then we'll go to the neutrons. Okay, so sounds good. Good. Now that's why I said I want us to just talk about this as a story, because most times students battle with who did this, who actually found electrons, who did not. I'm like, no, there's nothing to cram about this. All you need to do is just look at it, tell your story, let it flow like a tells, you know. Let it flow like a story. Shouldn't cram anything. Should be able to know who did this, who did this, who did that. You need to know. Yeah, nobody is asking you to explain this J.J. Thomson's experiment with the that I did now. You can comfortably, even if it's not too perfect, but you can say it to some extent, you know. So the cathode ray experiment, you can actually explain it. So I think we have to call it a day. So I think I just have one more class with you, and that will be next year, and I will be done with you. Another lecturer is going to take over from me. So next year, we'll look at how we're able to get our neutrons and the proton, because that is number 3. We already know who actually proposed that atoms are, you can have isotopes of an element. Is there any question before I sign out? Any question? Stop writing your names. Any questions so far? Are you guys good? Yes or no? I don't know. Ask them why the matric number is flooding in the group chat. So ask them again. No. Okay. So thank you guys. Enjoy your Christmas. Enjoy your holidays. But please don't forget to read your books. Again, if you have not registered for CHM 107, quickly come and do that now with the technologists in the lab, chemistry lab 101, 102, 105. I think that's where they are registering students. Make sure you register before you leave campus today. Make sure you register for your CHM 107. And do have a nice holidays. I'll meet you in January to wrap up with the class, and we just have few of the slides to look at. But please do not go and eat rice and forget my class. Remember, we didn't start with questions today because of time. Next class, we'll be taking a lot of questions while we are concluding the class. Thank you all. I love you all. Stay good and be happy. Bye. So I'm going to meet you, all of you now, to say your bye if you want to. It's not by force. So I'm going to unmute. How did they even? Okay, no. I want to allow participants. Okay, you can now mute yourself.
Bye.
Okay, bye.
Thank you, ma.
Thank you, ma'am.
You're welcome.
Merry Christmas and New Year.
Bye-bye,
Merry Christmas and Happy New Year in
Thank you,
advance.
ma'am.
Ma, Merry Christmas and Happy New Year.
Merry Christmas to you all.
Merry Christmas.
Bye.
Bye.
Don't
Merry
forget
Christmas
to
and Happy
read
New
your
Year.
books. So year
Bye.
one is
Bye, ma.
year one is MCQ, multi-choice questions. So it's trickish. Read and read it.
Look at Ebuka.
Don't try anything.
Yes.
So bye. That will be all for now.
This class.